Hi there, and welcome back to Triplicate, and today we are going to look at digital filtering, and specifically a type of filter called a finite impulse response filter, which is a bit of a tongue twister, so it's generally known as an FIR filter. So when people start talking about FIR filters and how they work, they tend to start talking about z-planes and the square root of -1 and getting into some reasonably heavy mathematics. Now I always try and think of things in a way I guess you can get your head around that means something intuitively, musically, because you can do a bunch of mathematics, as I say, involving the square root of -1 and z-planes, and get the answer out. And if you're designing a filter for, I don't know, an aircraft control system, that's what you want to do because you want the precise answer. But I always find if we're doing something intended for a musical use, you want to get some kind of a feel for what's going on. So this is the way I developed of understanding how an FIR filter works and calculating the various parameters you need for it from the filter response you want. Okay, so essentially an FIR filter consists of a delay line. So our input samples come in here, and we have a delay line which just stores the samples. So the most recent sample is here, and when we get a new sample they're all shuffled down one. And so on to the last one. So if we call our sample value x, we have x in here, x minus 1, x naught, x minus 2, x minus 3, where these minus 3s are the sample number and the current sample's naught, x minus 4 to x minus n. And what we do to form our filter output is we multiply each of these by a number. So times A0 times A1 times A2 times A3 times A4 and 2 times AN. And we simply sum together all these scaled values. And that's our input, and that's our output. So that's pretty straightforward to calculate. There's a few calculations, but they're all simple depending on how long the filter is. But what we need to know is these coefficients, these A numbers. Assuming we know a filter response, then we need to know these A numbers, and that is possibly the hardest part of an FIR filter, is calculating those. Okay, so let's consider the case of a very short filter. We will just have 5. I'll draw another one there and another one there. And we have our sample which travels down this delay, Okay, and let us consider, well, we have A0, A1, A2, A3 and A4. And let us consider a waveform which is repeating, I'm going to draw it up here, and consists of a sample of 1, and then 0, and then 0, and then 0, and then 0, and then 1, and simply 0, 0, 0. So these ones are going to travel down here every sample, and then when that one comes out the other end, another one will come in here. So our output will be in sample order A0, A1, A2, A3, A4, A0, A1, A2, etc. Okay, so here we're going to be doing some Fourier analysis and synthesis, and basically what this says, and again you can look it up, there's plenty of resources on the internet. For Fourier analysis we can analyse this waveform as its frequency content. We can say this consists of a sine wave at this frequency, a sine plus some level of a sine wave at half this frequency, a third the frequency, etc. And we know what we want this filter to do in harmonic terms. Obviously this is why we're applying a filter, because we want to do some specific filtering job. So if we know the harmonic content of this waveform, we can then simply apply our required filter to that to come up with the output waveform. And that output waveform is, we know, A0, 1, 2, 3, 4, A0, 1, 2, 3, 4. We can use Fourier synthesis to generate this output waveform, and then our FIR coefficients just drop out at the bottom. So let us see if we can find out what the harmonic content of this repeated pulse is. Okay, let's do some Fourier synthesis with some cosine waves. So here we have one cosine wave. We've got 2.5 cycles of it. So let's now go up to doing Fourier synthesis with 5 cosine waves, all the same amplitude. And as you can see, we are starting to get what looks like our little pulse wave. So that's very encouraging. But there is something we need to note here. We have a little DC offset. What looks like our sort of average zero level is below 0, and we'll come back to that. So here we've got 25 harmonics, and as you can see it really is looking like our little pulse wave. So I think we're on the right track here. So let's just go up to 50 harmonics. Yes, just a little bit of wobble, slightly below the 0 line. Apart from that, just pulses, and up to 100 harmonics. There we go, we just get pulses. So that's good. We know the harmonic content of our pulse waveform. It is just all the harmonics at equal amplitudes, which makes life very easy when we're calculating our filter. Right, well, before we can calculate some coefficients for our filter, well, we need to decide what we want our filter to do. So here is a completely arbitrary filter characteristic, linear 1 from 0 to 1 going up and kilohertz across. and we are going to use a FIR filter of 48 coefficients. So that means the bottom frequency, one cycle in the coefficients, is 1 kilohertz, which just makes the things a lot easier to visualize and to see. So this is just something I've entirely made up for demonstration purposes. So the dots are at 1 kilohertz, and these are the numbers here. The program will come to the actual numbers for each kilohertz. So we need to, by Fourier synthesis, to create one cycle of a waveform that has those 1 kilohertz waveform that has those particular levels of harmonic. So I have taken these numbers here and here we go, put them into an array called filter 24 for no particular reason. So this function, generate coefficients, takes our filter characteristic that we just looked at, i.e. that list of numbers, and turns them into a list of filter coefficients. So for each of the filter coefficients, we first do the static amount, which also includes everything up to 1 kilohertz. I'll show you that on the graph later. And that is 0.5. That's just the number I've discovered to give the right output. I've never looked into the mathematics as to why that's 0.5. So now we go from the harmonics, through the harmonics which we get from our filter characteristic. So we are going to do Fourier synthesis, and we're going to use a phase value of the coefficient number, so we're going through the wave, times the harmonic number, which gives the frequency. So if the harmonic's 2, the phase will go up twice as fast than if the harmonic's 1, and we divide by the FIR size, so that phase is in cycles. We subtract a half just so the peak value is in the middle. That I've just really done this to make the graphs look a bit neater, that I will show you anon. Now this is a tricky bit. Again, I do not know the mathematical reason why this needs to be done, but each coefficient needs to be in a different phase. So if the harmonic number is odd, we subtract the this particular cosine wave from the total coefficients, and if the harmonic number is even, we add this particular waveform. Again, I haven't looked into the mathematics as to why you need to do that. Just really want to get something working rather than do a lot of mathematics. Far more fun to make a noise. So when we've done all the harmonics, we divide the thing down by 2 over the FIR size, in this case 48, and that just scales it nicely, so the output is the same size as the input. Okay, and there we just print it out, so I can make pretty spreadsheet graphs of it. Right, we have our coefficients. Should we see how we implement the filter? So here is our delay line, which is a series of memory locations. There it goes. Off to however many we have. Now, when I initially described how the FIR filter worked, I showed the input going into here and then everything being shuffled down one, but that would be ridiculously inefficient in terms of coding. So what happens, we have a right pointer, and every time a new sample comes in,
it moves down one, and then when it gets to the start it moves back to the end. So let's say we have our right pointer here, and let's say we have our coefficients here, which is just another array in memory: A0, A1, A2, A3, A4, A5, A6, etc. So then we have a read pointer which we set there, and at the starts at the right point, the most recent written. And we have another pointer through here, so we take that one, multiply that by that, and add it to the sum. That by that, 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 and comes round. And when we get to the end here, we start again at the beginning. So if we assume that's the sum total, so we've got what, 7 elements. So if that's x0, x1, x2, x3, x4, x5, x6, in this case we would have out equals a0 times x3 plus a1 times x4 plus a2 times x5 plus a3 times x6, and then this one loops round, so we have plus a4 times x0 plus a5 times x1 plus a6 times x2, and that's all of them. And then the next sample, this would move down one, a new sample would be written there, so that will be then be the newest, the second newest, the third newest, first, and we do it all again. So that way we're just moving pointers, not shuffling data down memory locations. Okay, and a quick look at the code. So FIR filter is our filter elements. So we save the new input, we set the read point to the right point, we set the sum to 0, and for each size, each element, we scale the filter value at the read point by the filter coef, that's I, and I is, steps through the filter coefficients. We add one to the read point, and if the read point is past the end, then we set the read point at the start. And then finally we decrement the write point so that the next sample goes into the right place. And if the write point is less than 0, we put it back to the end. Now, the point here, usually in code, doing an if is quite inefficient because they have pre-fetching of instructions, so you lose a cycle because it doesn't know which way it's going. So it's better to use a FIR of a size which is a multiple of 2, say 64 instead of 48. So then the pointer, when you increment the pointer and then just AND it with 63, so if it's 64 you'll get 0, which is a lot more efficient than, as I say, doing an if. Just a heads up on that one. And how does it perform? Well, here it is, and the bottom trace is our filter that we were trying to create, so not too bad. We'll look at it directly against the original in a minute. And the top trace is just a low pass filter, just trying to make a low pass brick wall low pass filter at 11k or so, just to show you how that happens. And this is typical of FIR filters, this sort of bobbling tail where you actually want 0, and also this wavy stuff is. So let's have a look, see how this waveform compares with what we actually wanted. Well, here it is. So the blue graph is what we wanted, and the orangey red graph is what we've got, so that's not actually too bad. Just a quick note that the glitches like that one are my measurement of the amplitude, which isn't 100% perfect, so they're not actually happening in the output. Okay, so I chose a 48 coefficient filter just for ease of being able to, so each one was a kilohertz. But how does the length of the filter actually affect the filter's filtering? Well, here we have on the top we have our 48 point or length or whatever filter, and on the bottom I've done exactly the same filter but with 96, twice as long coefficients, and you can see the transitions between the levels are a lot sharper, and you can see the waviness on what's supposed to be a straight line is twice as fast. So you do get better results the longer the filter is, but obviously the longer the filter is, the more processing it takes. And if we look again at this, the first point we could specify apart from 0 Hertz DC was at 1 kilohertz, so we can say nothing about what happens between DC and a kilohertz, and a lot of musical stuff happens there. So if we wanted to go down to say anything about what happens at 100 Hertz, we'd need a 480 coefficient filter, and since we've got to do a multiply and accumulate per every coefficient, even with a DSP MAC instruction, multiply and accumulate instruction, that's 500 instructions, so it would make the filter quite processor heavy. So FIR filters are certainly at their best for high frequency applications. Okay, now we have our FIR filter. Let's consider a couple of slightly different applications we can use it for. Firstly, let's implement a low pass filter. So we have, just for ease, 5 elements in our filter, and we are going to just take the DC component of our filter. So that will be DC, and at the first coefficient, which is the sample rate over 5, that low pass filter will have gone to 0, and it will in theory be 0 all the way up from there, and in practice no, we will see it's not the case, but let's just have a look, see what we're doing. So here we have x0, x1, x2, x3 and x4, and what we're going to do is use a constant coefficient of 1
and sum them all together. So the DC will come out, but no frequencies, as I say, above a fifth of the sample rate. So our current sample, the output, equals x0 plus x1 plus x2 plus x3 plus x4. The next sample, we will have everything's moved down the filter. Remember, in code this doesn't happen, but it's the easiest way of looking at it. We have x0, x1, x2, x3, and we'll call this x dash, our new sample. So for the next sample out, I've got a plus there instead of an equals x dash plus x0 plus x1 plus x2 plus x3. 3, come on, draw it. So if we look at these two, all we've done to get from that is added x dash and subtracted x4. And since we're using a pointer in a circular buffer, the pointer will go here x0 and x dash will go where x4 was. So all we need to do to get our new out is take our old out, subtract x4, add x dash and save x dash. So it is a very efficient piece of code. So let's have a look at the code implementation quickly. And here we have our implementation. So filter sum is our running sum of the running output value. So firstly, FIR filter is our filter. So we subtract the value at the right point, which is the old value we want to get rid of. We add our input value, which is simply sine wave I, because we're putting a sine wave into it. And then we save our sine wave I value and increment the right point. And here I have implemented the filters as being 2 to the n, so we can use a mask. So if the FIR size is 256, we AND it with 200, pointer with 255, which, as I say, is quicker than using if it's beyond the n, put it back at the beginning. And what kind of result do we get out of these? Well, you can see I've done 2 here with different cutoff frequencies, and this is the frequency of the sine wave here increases logarithmically over time. And you can see it's not a brilliant filter, in all honesty, but as I said, it's very easy to implement. Plus, these points where it is actually working efficiently are harmonics. So if we have, say, some zipper noise that is at that frequency, then these will conveniently take out the fundamental and the harmonics, which is one very good use for this kind of filter. And as I say, it's very efficient code wise, even if it does consume a fair amount of RAM to do. Okay, and let's look at another more creative use of an FIR filter. So here we have what I have called the Maverick Mangler, because it appears on the pulsar, and then I did a freestanding version as well. If anybody's interested, that would need to be converted to 64-bit. So if anybody's interested in actually having the Maverick Mangler on its own, get in touch with me and I will make a 64-bit version of it. Okay, we have here an FIR filter. In this case it's 256 points long, coefficients long, and we can see here I am calculating the coefficients using a random number generator, the CRAND function. So
that will give us a sort of random filter characteristic, which I'll show you in a minute. And here the actual Mangler filter is a standard FIR filter, as we discussed earlier. And I ran through this Mangler here, the a sine wave going from 20 Hz to 20 kHz or 50 Hz to 20 kHz, increasing in frequency logarithmically, and I did it for two different random Manglers. And this is the result, and as you can see, the filter characteristic is very knobbly, and you would think this would really affect the sound, but if you take an acoustic instrument like a guitar, the characteristic of the body is sort of quite knobbly like this, so it sort of makes it sound like more like a natural instrument, whereas a synthesizer tends to be very flat in its frequency response, if you see what I mean. So shall we have a look at the Maverick Mangler and see what effect it has? And it's called the Mangler because it mangles up the spectrum of the sound, I haven't mentioned. Okay, let's see the Mangler action on the piano sound. Firstly, with no Mangler on at all. Okay, and I generated 20 random sets of coefficients, 20 types of Mangler, the first 20 that came out of the random number generator. So this is the one that comes on the factory preset of this sound. And let's just run through a few others, just so you can get a feel of how they can sort of quite radically change the feel of the sound. Finally, back to no Mangler, just for comparison.
Well, that's it for this video. I hope you found it useful, and I hope it's managed to demystify FIR filters a bit. And if you're wondering why Triplicate has not been producing quite so much content this last month as normal, that is because so there we go, hopefully back on it now. So from now, it's goodbye from Triplicate. I don't know what to say now.
Goodbye.